Okay, guys, this is a lecture on boundary layers and how this plays a role in creating an environment favorable for thunderstorms. It's really, really important actually when it comes to that. So first thing I'm going to do is give you a little idea of how the atmosphere works. So here's the sun, right? The sun is the source of all of our energy, and it gives off radiation. And that type of radiation is short wave, or what we call visible light. That's primarily what it is. Shortwave, sometimes it's heat in infrared radiation, but this radiation tends to go through the atmosphere. The atmosphere is what we call transparent, and it's going to mostly go through the atmosphere where it's absorbed by the ground. Now, as a result of this, the air near or the ground itself gets warm. And so there's a couple of things that happen. The Earth generally gives off radiation that sometimes is absorbed or partly absorbed by the atmosphere, and others of it goes out to space. And the atmosphere absorbs radiation, and it can give radiation to space. Some of the radiation can be given back to the Earth, and this is what we know as the greenhouse effect. I'm not really going to talk too much about the greenhouse effect. But this radiation that comes out from the Earth and atmosphere is known as OLR. Notice I've drawn it differently than what's coming in, and that stands for outgoing long wave radiation. Okay, so radiation coming out. And this is an important term that we're going to use many times later on in class, outgoing long wave radiation. So that's what's going on with radiation. That's not really what I want to talk about in terms of boundary layers. But I want to look at this example here where the ground is warm and the air above it is not as warm. Okay, so there's a difference in temperature. And anytime there's a difference in temperature, I want to think about the need to transfer heat. Now, radiation is one of the ways of transferring the heat, and that's what we've got here. One of them is convection. Convection is what we've been talking about in the atmosphere, where the atmosphere mixes up. And we're certainly going to mention convection. But since it's part of the fluid that's being redistributed, then I need to go from the ground, the Earth itself, which is not part of the atmosphere, to the atmosphere. And the only way to do that is to give off something which we call sensible heat. Sensible heat is heat through contact, and contact refers to conduction. So I know we've mentioned this before. Conduction is one of the three methods of transferring heat. So we need the air to get warmed by coming in contact with the ground. So then the question is, if the air is cooler than the ground, and we have this transfer of sensible heat, exactly how much of the air is going to know that the ground is warm? How thick is this layer? And the answer to that is astoundingly only about a centimeter thick. Really, really, really small. Okay, now this arrow is going to be called a sensible heat flux. So I'm going to introduce this term, flux. Flux is a flow through an area. So what I want you to think about is that there's actually this sense that heat from the ground is flowing into this really narrow layer about a centimeter thick. Well, what is this layer called? This layer is called the molecular boundary layer. Okay? Molecular boundary layer. And so what happens is this air in this layer gets really, really warm. Well, now what happens to it? I want you to think of this layer as a parcel. Okay? And the question is, why will this parcel rise? Well, we've always said the pressure or the The parcel will rise if the density is less than what? It's less than the surrounding air. So we always compare it to the surrounding air. But notice this time, it's not just a parcel surrounded by the atmosphere. It's the entire layer of atmosphere. So this parcel and the parcel next to it and the parcel next to it, or the air next to it, is all the same temperature. So now we have to say, well, is there another reason it could go up? The answer to that, and this is kind of the weird part, you have to really think about what I'm saying here, is it needs to be not less dense than the air around it on the outsides horizontally. It needs to be less dense than the air above it. So imagine that I had vinegar and oil sitting there, and I put oil and then I poured in to a jar of vinegar up on top. The oil is less dense, and it's going to bubble up through the more dense fluid and come back down. So if this air, and this is really important to write down, if the air in the molecular boundary layer is less dense than the air above it, it's going to start overturning. That overturning, where this air goes up, and because some air is going up, some air needs to come down to take its place. It overturns. That is what we call mixing, which is overturning. But notice it's doing this by itself, so we're going to refer to this as autoconvection. Like if I took spoons, I could mix up that air. But I'm just saying it's going to do it all by itself because the air in the molecular boundary layer is less dense than the air above it. Okay? So I want you to think about that. I want you to write that down. So go rewind the lecture and make sure that's in your notes. So then the question is, what makes density change? What two things affect density? Well, the ideal gas law says that pressure is related to density times this constant R times temperature. So the ideal gas law says that there's a relationship between temperature, density, and pressure. If you know nothing else about the ideal gas law, I want you to know that pressure, density, and temperature are all related. Okay? So this is super important. Pressure, density, temperature are related. Okay? So I want to make the density less. Now, what I'm going to say is this. When pressure goes down, the density goes down, generally speaking. Right? So if I go higher in the atmosphere, do you agree that air pressure is the weight of the air above you? There's less air, therefore there's less pressure. Do you also agree that going up a mountain, the air is going to be less dense? That's why it's sometimes harder to breathe. You get less oxygen in your lungs. So when the pressure goes down, the density goes down. But what else can make the density go down? Well, it can go down if the temperature goes up. Okay? So what I want to say is that the density can be made lower if the temperature is warmer or the pressure is lower. So let's go back to our molecular boundary layer. Molecular boundary layer. And I want to think about the density here in it versus the density above it. Remember, this is the Greek letter rho. Remember, we've talked about this before. It's not a P, it's a smooth line. So what affects this? Well, if this density is going to be less, needs to be less and more, then it needs to be under less pressure. But do you agree that it's actually the air here is under more pressure? There's more air above this layer from there than there is from here. So if I just think about pressure as in terms of the weight of the air above me, there's going to be more pressure down here than up here. Oh, so that would make it hard. Okay, what else happens? Well, the temperature in the boundary layer, in the molecular boundary layer, is warmer. So because it's warmer, it would be less density. So this air is more dense because the pressure is higher. But it's less dense because the pressure, because the temperature is warmer. So the air in the boundary layer is warmer than the air above it. That makes it less dense, if that were the only thing worrying about it. But it's more dense because the pressure is higher. So do you see that I'm fighting? Temperature, the effects of temperature here are to make it less dense if it's warmer, but the effects of pressure is to make it more dense. So what I'm saying is that the effects of temperature being warmer have to compensate for the effect of more pressure causing a greater density. And you have to think through this about what compensation is. So I always ask my students, I said, you have a boat in the water, and in the bottom of the boat there's a hole, and there's water coming into the boat. Will the boat sink? Well, here's the question. If water starts coming in your boat, you're in the middle of a lake and water's coming in, what would you do? Well, you should bail the water out. So the way that you think about this is, will the boat sink? And the boat won't sink if you can bail out enough water to compensate for the water coming in. That's how I use the word compensate. So there's a compensation going on between one thing, water coming in, and another thing, water coming out. Well, the same is true with density. It's affected by a higher pressure. It's compensated by a higher temperature, both of which are impacting density. So what I'm saying is the temperature needs to be warmer than this. Temperature has to be warmer than here. Than here by a certain amount. So the temperature is dropping. It's warmer going to cooler. It needs to be warmer enough than over here. So I don't know if this isn't, that's than, okay? So let's do this. Let me get rid of this and tell you when that happens. Well, it's the temperature changing with height, which makes it a lapse rate. And we're going to call this the autoconvective lapse rate, which is 34 degrees Celsius per kilometer. Now I want you to think about this number. That seems huge, doesn't it? 34, I mean the dry adiabatic lapse rate is 10 degrees Celsius per kilometer. You're telling me that the air has to drop off by 34 degrees Celsius per kilometer for that air to overturn all by itself. That seems a lot. Well, let's think of some examples. When would I get a huge cloud that could be man-made? Well, imagine that I detonated a nuclear bomb. Super hot air, the air becomes super warm, very low density, and the air will start to rise all by itself. And you get these big mushroom clouds. So that's autoconvection because we heated the air to thousands of degrees because we released the nuclear bomb, okay? That's probably not going to happen in a thunderstorm. Although if you had a nuclear bomb, you'd probably get thunderstorms around there as well. But 34 degrees Celsius per kilometer, I want to think about what that is. Okay, the first thing is 34 degrees Celsius per kilometer is 1,000 meters. if I make this, it's 34 degrees Celsius or 3.4 degrees Celsius over 100 meters. That's the same lapse rate. So this is all the autoconvective lapse rate. But I could also do this. It's actually 0.34 degrees per 10 meters. But wait, it's actually 0.034 degrees per 1 meter. I need to do it per centimeter. So what I'm saying is this is actually going to be 0.00034 degrees Celsius per 1 centimeter. Now, think about that. The sun comes out, the pavement very easily can be 0.00034 degrees Celsius in a centimeter. That's nothing. So in other words, as soon as the sun comes out, the air in contact with the ground in the molecular boundary layer will almost instantly start to overturn. And you start to get convection. And what convection does is it takes the heat, the excess heat from this layer, and it mixes it up to here, and then this air comes down and replaces it and heats it. So in essence, conduction through the sensible heat flux is only heating this much, but then the atmosphere starts to overturn. That overturning, these are called turbulent eddies. And you could go online and look at turbulence. When people exhale smoke, it tends to go out and become turbulent. In fact, if smoke goes out smoothly, and then it becomes turbulent like this, right? So think of smoke, somebody exhaling smoke this way. This flow is called laminar, which we've used before, smooth, and this is turbulent. So listen to what I'm going to tell you. The two types of describing fluids motions is laminar and turbulent. Okay? So this autoconvection creates turbulent. If you think of this as being like one big thing going up and something coming down, we call this an eddy, E-D-D-Y. These are turbulent eddies. Now these turbulent eddies are a result, they're what we call thermally induced turbulent eddies. That's what these are. And these eddies redistribute heat. That's what they do. And they're redistributing heat within part of the atmosphere. And the question is, well, how high do these eddies go? Now, if you ever watched a bird soaring, like a vulture or maybe a hawk, sometimes they soar way up very, very high. These eddies can go up a couple of kilometers in the middle of the afternoon. So they're really big. And those eddies are the fact that we've heated the surface, the ground heats this small layer of air, and then we redistribute the heat throughout a deeper layer of the atmosphere. So what I'm going to say is this. This layer is known as the CBL, which stands for the convective boundary layer. We can write that out for you. You can write it out. Convective boundary layer. Sometimes we call it the PBL, and P stands for planetary. Planetary boundary layer. Okay? So that planetary boundary layer, or the convective boundary layer, is where the eddies dominate. What kind of eddies in this case? Thermally induced. Getting the idea that there might be other types of eddies? That's true. So the question is, what do eddies do? They redistribute heat. Now I want to stop and just have a little conversation with you. And it's kind of coming close to lunch and I'm kind of hungry. So here's what I want you to think about. I'm going to cook up a big pot of spaghetti sauce. And I have this big pot, and I turn on the heat to heat up the spaghetti sauce. Do I just turn on the heat and let it go? Is there anything else I need to do? And the answer is, I need to start stirring it. Because in the stirring of the spaghetti sauce, I'm going to take the heat from the bottom and bring that hotter spaghetti sauce up and replace it with cooler spaghetti sauce, and then I'm redistributing the heat. So what's the purpose of a spoon? Is to redistribute heat, okay? What's the purpose of a turbulent eddy? To redistribute heat, just like a spoon does. But now the question is, what would the temperature in a pot of spaghetti look like? What would the temperature profile be of this pot of spaghetti? So what I'm going to draw here is, imagine I've got a big pot, it's a square pot, and I've got, I'll use red because it's spaghetti sauce. Spaghetti sauce. And if I've mixed it up completely, so I'm actually have accomplished this, do you agree that the temperature here and the temperature here would be the same? If the temperature is everywhere the same, we say that it is isothermal. So the temperature profile is isothermal. Okay? Now the spaghetti sauce obviously is just a couple of inches thick. But you would say that, wouldn't you? That's what you would assume, and you'd be right. That is true. Oops. What if I did this though? What if instead of spaghetti sauce, I call this air? Would the temperature up here be equal to the temperature down here if I redistributed the heat? In other words, what is the temperature profile of a well-mixed layer of atmosphere? So this time you can imagine that this is, oh, I don't know, I'll use this number for a reason, that this is about 1 kilometer. So would this temperature here be the same as that? The answer is no. And that's because the air up here is expanded out because of pressure drops, right? This is not. Is temperature a measure of heat? So there's the question. Is temperature a measure of heat? And the answer is no. What is the measure of heat? And you should say this. The answer is potential temperature, theta. So in spaghetti sauce, we said isothermal. The temperature is the same everywhere. But in the air, it's not the temperature, it's the potential temperature. But the potential temperature, everywhere the same, is called isentropic. And another way to think about an isentrope is that the temperature is dry adiabatic. That's important, which means if I mix a layer of atmosphere, that temperature profile will be dry adiabatic. If the temperature profile is not dry adiabatic, then I know it's not well mixed. So when I look at this, I'm like, what is that level? That level is the top of the CBL, the convective boundary layer, or the planetary boundary layer. And the reason we know that is because below it, it's dry adiabatic. Above it, it's not. Now guys, listen to me. This is the environment. This is the environment. This is not a parcel. This is the environment. So this is what's happening in the atmosphere when the sun comes out. It starts mixing the atmosphere, and then a layer of the atmosphere becomes dry adiabatic. This is the atmosphere. And we said instability is a race between the parcel and the environment. We want the environment to win. That means we want the environment's lapse rate to be as big as possible. 10 degrees Celsius per kilometer is really, really steep lapse rates. And as a result of that, I can say clearly, unequivocally, this is the case. The most unstable layer of the atmosphere is the planetary boundary layer. And if you think about it, the parcel goes up. The parcel, being in blue, would start at the temperature and go up dry adiabatically until the LCL. So notice that in the race to get cold, they're getting cold at the same rate. Now, what about the dew point? Well, here's something else, right? We talk about the dew point, and then or the mixing ratio, right? We get a mixing ratio line. And the mixing ratio is the amount of water vapor in the air. Would you agree, if I've got water vapor in the air and I've got big spoons, or in reality, turbulent eddies mixing the atmosphere, wouldn't I create a distribution of the amount of water vapor? So in the boundary layer, we tend to get a constant mixing ratio profile in the dew point. And if you remember, that shows us the dew point lapse rate, which is 2 degrees Celsius per kilometer. And the dew point lapse rate says that the mixing ratio is constant. And so the mixing ratio would go up this way, and then we get to the dry adiabat going to this point. And so now the top of the boundary layer is also maybe the LCL. So here's the parcel going up. And then when we go up here, the question is, what do we have? Is it going to be unstable or stable? And the answer is, I don't know for sure, but I have a cloud at the top of an eddy. So what that's going to look like is I'm going to see a little bit of a cumulus cloud. When I see in the middle of the afternoon a little dot of cumulus, that's a cumulus. If you remember what it was, do you remember? Cumulus. And it's a fair weather cumulus. So anytime you see a dot of air, or a dot of cloud in the air, you are telling me that you've heated the air, and because of heating, you now have a boundary layer cumulus cloud. But if you look at how things are found, then not only is the top of the CBL where the clouds form, that's known as the CCL, the convective condensation level. And that's what happens in the atmosphere. That happens in the spring and summer all the time. Starts out sunny, and then all of a sudden you dot the sky with cumulus clouds. So really, this is all a result of what's going on in the boundary layer. That's how this works. Now, at night, there's no heating. So instead of having an upward flux of sensible heat, what do you think happens at night? Well, the ground loses energy through OLR, outgoing long wave radiation. It gets cold. Air comes in contact with the ground, and the air gets colder as it puts heat into the ground. So there's a downward flux of sensible heat. Problem is, once the air in that small layer gets cold, do you see that there's no reason for it to mix up by itself? It's not auto-convecting. So the air gets cold right at the surface. Imagine that you go outside, the air temperature up at your face is like 40 degrees. But at the ground, you start seeing frost. And that's because the ground temperature is below freezing. And when the ground temperature drops below freezing and the air temperature is still warmer, any air coming in contact with the ground can drop temperature and you get to frost. If it's cooler, then you get dew. So the temperature drops to the dew point. If its dew point is below freezing, then it's frost. So that's what's happening at night. And that's why we don't see fair weather cumulus clouds at night. They're only there during the day because they come about by heating from the sun. Okay, so the eddies, the purpose of the eddy is to redistribute the heat. It's also to redistribute or to make constant mixing ratio. So when I look at a sounding, generally speaking, a sounding is going to be, I'm going to have a layer of dry adiabatic followed by something else. And then I'm going to have a constant mixing ratio line followed by something else. And when I see a sounding like this, I know always that that is the top of the boundary layer. Again, there's no parcel on here. Now in this case, if I put a parcel on here, I'd go dry adiabatically till it intersects the constant mixing ratio line, and there would be the LCL. But notice that the air would be stable up at the LCL, and so the air doesn't create clouds. So some days, and I'm looking out here on a cold day, there's no cumulus clouds because the air is stable. Okay. Now, imagine that I were to make the temperature go warmer. So what I want you to think about is this, is I'm going to increase the temperature at the ground. Sun's out, it's warming up, warming up, warming up. Okay. What would that do? Would I get clouds because I'm going to warm it even more? No, but the temperature may go to here, and then the temperature is going to go up dry adiabatically to there. So I'm basically saying that the eddies are this tall originally, and now they can go up here. There's nothing stopping them from going all the way here. So if I look at a graph of the height of the CBL versus time, and here I'm going to look at sunrise and sunset. Once you get sunrise, you start heating the ground, and the boundary layer starts to get higher and higher and higher and higher. Now the sun sets, I no longer have this, and so something is going to happen. I'll get there in a sec. But what I'm saying, and this is what you should write down, is during the day, the boundary layer becomes higher and higher. I start mixing air higher and higher. So this dry adiabatic part of it will go higher and higher, so that the sounding looks like this. But if I do that, if I start to mix the atmosphere with big eddies that are doing this, do you understand that I'm bringing air into the boundary layer? That's a lower mixing ratio. So the average mixing ratio is going to go down, at least in this case. So it's going to go up to maybe here. That's the new mixing ratio because I keep mixing dry air down into the boundary layer. So what does that mean for the surface dew point? As you heat the ground and mix drier air, you should start to see a drop in the dew point. Now the difference between the temperature and the dew point is called the dew point depression. That's going to get bigger and bigger. Temperature's going up, the dew point's going down, the LCL is going to go much higher. That is not a good sign if you want severe weather. So the question is, how do you stop this from going lower? And there's two things you consider. What if the dew point above the boundary layer was more? What if the dew point came up like this? Well, then I'd be mixing moisture down. That happens with fronts where I'm actually mixing moisture down. So I can do that on occasion. I'm not going to talk about that with you guys in this class, but I'm bringing dry air down. So how do I compensate for that? I'm mixing dry air down. How do I stop the dew point from crashing? And the answer is, I need to bring in moisture from somewhere else. Well, what do you call the bringing of moisture into a region? That's called advection. Now you should remember on the static stability handout that I gave you, it says positive moisture advection either at the surface or within the boundary layer. So if I'm mixing dry air down, I need to compensate by instead of losing the moisture, I need to bring it in from somewhere else. We know that around here, the majority of the water vapor that's in the air is coming from the Gulf of Mexico. So if I have strong southerly winds, I'm bringing in a lot of moisture. I compensate for mixing by replenishing the low-level moisture by bringing that air from somewhere else. So that's an important aspect of what's going on here. So review this, make sure you get this. Now, you're talking about one more thing here, and that is, well, what happens when I've got nighttime? Can I mix the air any other way? And the answer is yes. So if I think about nighttime, what else mixed the air? So I'm going to draw a little city here. There's some buildings and houses and that kind of stuff, right? There's a city. And then over here, there may be some trees. Maybe I've got a little bit of a forest. Over here, those are trees. I don't know if they look like trees. And then over further away here, I might have some mountains. Okay? Anytime the wind flows over this terrain, the rougher the terrain, the more that the air gets mixed up. So when the air hits buildings, it starts to become turbulent. Over trees, over forests. It becomes really turbulent over mountains. So wind flowing over a rough terrain causes turbulence. Those are called mechanically induced turbulent eddies. So my students a long time ago, and this is not an official scientific thing, but I kind of like the creativity of my students. We have tights and mites. So mites and tights. Mechanically induced turbulent eddies, thermally induced turbulent eddies. And this is a result of wind speed. So stronger winds are going to create bigger eddies and roughness of the terrain. And that's actually the word we use. So that boundary layer, when I look at a height, can be maybe around 500 meters. Over a mountain, it can be more. Mountains are really rough. What's the smoothest surface that there is on the planet? Do you guys know what that is? If I were to ask you what's the smoothest surface? And the answer is water. Water, and the only reason it's not perfectly smooth is because the wind is actually creating the waves. So it gets a little bit chopped up because the wind is doing that. But for the most part, the air in the boundary layer gets mixed up over water for a very small area that's only around 200 meters. So it's much smoother flying over water than it would be if you're close to the ground than it is over land. So airplanes coming in, when you get near the ground, they tend to be bumpy. That's turbulence. And during the afternoon, during the day, you're going to get lots of turbulence. At night, you're going to get turbulence right before you land. If you come in over the lake or over an ocean right before you land, you're going to feel nothing until you get over the land, then you're down. So flying over water is a much smoother thing than flying over land. So I want to think about this over here as being like a constant boundary layer height at night. So this, let's define how this is. This is what we call the nocturnal boundary layer, which is dominated by mites, mechanically induced turbulent eddies. That's what happens during the day. You might still have that at night, but these eddies get way bigger. And let's say on average, maybe 1 to 2 kilometers thick. So during the daytime boundary layer, they're dominated by what? By tights. Okay? So during the night, they're dominated by nocturnal, in the nocturnal boundary, dominated by mechanically induced turbulent eddies. During the day, they're dominated by thermally induced turbulent eddies. So the boundary layer gets higher and higher during the day. Well, this, folks, is the time where I'm going to get the best chance of thunderstorms because I'm making the lowest part of the atmosphere as unstable as possible. But what happens over here when I go from night to day? These were turbulent eddies that were there during the day, but now they disappear at night. So this layer here is what we call the residual layer. They were affected and in essence slowed down during the day, and they rebound at night. They go back to laminar flow and it establishes down here. And the most important thing that happens is you get an acceleration of the winds in this layer. And that's what's known as the nocturnal low-level jet. Nocturnal low-level jet. Or you could, I've also, maybe it's this way, low-level nocturnal jet. I don't know what's better. But that's what it refers to. And so at night, you get these stronger winds, and that oftentimes creates a much more favorable environment for tornadoes if the air is still unstable, and certainly for big MCSs or MCCs coming in later, because you start getting stronger winds, the shear goes up, and things get really nasty. A lot of times when we're out storm chasing, we have what's called the 8 o'clock magic, is that if we get thunderstorms around 8 o'clock in the evening, right as this low-level jet starts to take over, we start to get some really big tornadoes. Now, as you go into the overnight hours, it can become more stable because you're cooling the boundary layer. So the boundary layer, you want it warm, but if it's too warm, you don't get the amount of shear that maybe you'd want to have. So there's all sorts of complexities that you deal with in real life, but that's what's going on here. Sometimes the air near the ground, when this happens, stops almost completely. There's no wind speed. That's called a decoupling of the boundary layer. So if you've ever been out there, it's kind of windy, and then all of a sudden you go out about 9 o'clock at night, it's like, wow, there's no more wind. I do a lot of walking on cold days, and I don't want to do that. So if I wait till the night, the wind tends to die down more because they get calm in the evening oftentimes. Not always, but sometimes. And that usually makes it feel a little bit better. So that's a decoupling of the boundary layer. Just be aware that you're going to see that. Okay? That's what's going on with the boundary layer. Just in review, you've got two types of eddies, thermally induced and mechanically induced. Mechanically induced comes by the winds over a rough terrain. Thermally induced comes from autoconvection with this sensible heat flux that causes a redistribution of heat and water vapor content, or the mixing ratio. It's the most unstable part of the atmosphere, and at the same time, it's going to create an environment favorable for thunderstorms. However, as it shows here, if you mix the air too much, you can bring dry air down, and that's bad for thunderstorms. But if I can keep moisture replenished by advection, positive moisture advection, then I have a much more favorable environment, and I can eradicate the cap that may exist. And that's how the atmosphere works. The next time I'm going to talk about different types of soundings, and we're going to talk about something called an EML. I can tell you what it is right now, and how it comes from the boundary layer of this. But that's our lecture on boundary layers. Please take good notes on this. It's really important to understand the intricacies of how thunderstorms actually form. And with that, I'm going to hide the ink, stop the share, and end the lecture. So have a great day, guys.